If a function f is twice differentiable at x0, then x0 is a relative maximum if f prime of x0 is equal to 0 and f double prime of x0 is less than 0. And x0 is relative minimum if f prime of x0 is equal to 0 and f double prime x0 is greater than 0. If f double prime of x0 is equal to 0 or f is not twice differentiable, we rely on the first derivative test. Relative extrema using second derivative test. Given a function f of x equals to x cubed minus 3x squared, we use the second derivative test to find the relative extrema of this function. The first derivative, f prime of x, is equal to 3x squared minus 6x. Taking 3x as a common factor, we have f prime of x is equal to 3x times x minus 2. Set f prime of x equals to 0 to find the critical points. Setting 3x times x minus 2 equals to 0, we get x equals to 0 and x equals to 2. The critical points, therefore, are at x equals to 0 and at x equals to 2. The second derivative of the function f of x is equal to 6x minus 6. Use the critical points we obtained to evaluate the second derivative. The second derivative at x equals to 0 is equal to 6 times 0 minus 6, which equals negative 6, a number less than 0, which means there is a relative maximum at x equals to 0. And the maximum value is f of 0 equals to 0. Find the second derivative at 2, which gives 6 times 2 minus 6 equals to 6, a number greater than 0. Therefore, there is a relative minimum at x equals to 2. And the value is f of 2, which equals negative 4. Given a function f of x equals to x to the 1/3 times x plus 4. Rewriting the given function, f of x equals to x to the 4/3 plus 4 times x to the 1/3 by distributing the product. Using the power rule to find the first derivative, f prime of x equals to 4/3 x to the 1/3 plus 4 times 1/3 x to the negative 2/3. Taking common factor and rearranging, we obtain f prime of x equals to 4/3 x to the negative 2/3 times x plus 1, which is 4/3 times x plus 1 divided by x to the 2/3. The critical points are at x equals to negative 1 and at x equals to 0. Let's label the first derivative a. The second derivative is equal to 4/3 times 1/3 times x to the negative 2/3 plus 4/3 times negative 2/3 times x to the negative 5/3. Rearranging, the second derivative and taking a common factor, we obtain f double prime of x is equal to 4/9 x to the negative 5/3 times x minus 2, which equals x minus 2 times 4 divided by 9 times x to the 5/3. Using the critical points, the second derivative at x equals to negative 1 is equal to 4 times negative 1 minus 2 divided by 9 times negative 1 to the power 5/3, which is equal to 4 times negative 3 divided by 9 times negative 1, which is equal to 4/3, a number greater than 0, which means there is a relative minimum at x equals to negative 1. And the minimum value is f of negative 1, which equals negative 3. Since the second derivative fails at the critical point x equals to 0, we rely on the first derivative test. Using sign diagram of the first derivative, we plot the critical points negative 1 and 0 and pick test points in the open intervals formed by the critical points. Now we compute the first derivative at each one of these test points. F prime of negative 1/8 equals to 4/3 times negative 1/8 plus 1 divided by negative 1/8 to the power 2/3, which equals 4/3 times 7/8 divided by negative half cube to the power 2/3, which equals 4/3 times 7/8 divided by 1/4, which equals 14/3, a positive number, meaning the function is increasing in the interval containing the test point negative 1/8. Similarly, find the first derivative at the test point 1, which equals 8/3, a positive number, meaning the function is increasing in the interval containing the test point 1. The function is therefore increasing in the interval negative 1 to infinity, including negative 1. From the sign diagram, we see that the function has only one relative minimum, which is at x equals to negative 1. And this also happens to be the absolute minimum of the function from the graph shown here. Since the limit of the function as x goes to positive infinity is positive infinity, and the limit of the function f of x as x goes to negative infinity is positive infinity, which means the function has a minimum but no maximum on the interval negative infinity to positive infinity.